I recently did a video about paraboloids. If you'd like to watch it, the link is below, but you don't have to. The point is, in that video, I proved something for one specific parabola, and then I didn't bother proving it for all parabolas, and that should have annoyed a lot of you. Just because you've managed to prove something for one specific shape does not necessarily mean it generalizes to all shapes. In some cases it does, so all circles are similar. Once you have an identity for one circle, you can then apply it to any other circle. But let's say triangles. Triangles come in all shapes and sizes. They are not all similar. Just because you prove something for one triangle does not necessarily mean it applies to another triangle. And if you look at parabolas, they also come in all shapes and sizes. What a variety. How on earth can I show something for one parabola and assume it generalizes to all of them? Parabolas do all look different, but they are actually similar. The notion of there being more than one parabola is a lie. It's perpetuated by powerful mathematics teachers who have a vested interest. It turns out there is only one true parabola. Behold, there is only one true parabola. To prove that there is only one true parabola, let's start with its cousin, the circle. All circles are similar. So if I draw a circle on the board, close enough, in what way is that similar to, let's say, the circle of a pound coin? Well, if I get my pound coin nice and close, you can see it's possible to line it up so it exactly matches the circle on the board. For two shapes to be similar, you have to be able to line them up perfectly only by translating them around and making them bigger and smaller. Oh, and you're allowed to turn them over and rotate them, but that's it. When it comes to changing the size of a shape to show that it's similar to another one, you have to be a little bit careful. We need to scale it evenly in every direction. We can see this with three different rectangles. That 3x1 rectangle is similar to the 6x2 rectangle because it scales the same in each direction. Not to labor the point, but we're going to need this in a moment. If you scale up 3 by k to get 6 and you scale up 1 by k to get 2, the whole system works. For the same k, in both cases, we're doubling it. You scale from that shape to this shape, they're similar. Whereas this guy doesn't work. For these to be similar, we would need 3 times some scale factor k to be 4 and 1 by k to be 3. And that can't work. There is no k that scales both of these up to give you the new shape. You can't go from this rectangle to that rectangle without messing with its aspect ratio. Okay, enough rectangles, let's get on to parabolas. Translating parabolas is reasonably straightforward. If you want to move them up and down, you simply add some term on the end, which I'm going to call c. If I increase c, it goes up. If I have c as a negative number, if I'm subtracting, then it will go down. Sideways is slightly more complicated. Let's say we want to take our original y equals x squared parabola and move it to the side so it ends up sitting over here, and we'll say our new parabola is sat at some point d. So it's moved a distance of d across. If you've done this at school recently or possibly decades ago, you may remember you can adjust this equation to be y equals x minus d squared, and that has the result of just bumping it across d on the horizontal axis. We can even expand this out if we want to make it look a bit more familiar. Y equals x squared minus 2dx plus d squared. There's our new parabola that's been moved to the side. The important thing to bear in mind in both of these cases, going up and down and going side to side, combinations of which will get us anywhere we want on the surface, is that neither of them change that lead term. You always have a x squared out the front. The other terms after the x squared are what control the position of it on the plane. What this means is for a completely general parabola, y equals ax squared plus bx plus c, the end bit, the bx plus c is just a big bit of machinery for moving it around. The only thing that actually changes the shape is the ax squared out the front. Actually, you know what? Maybe I've made a mistake. Because even if you accept that the plus bx plus c moves parabolas around the plane, and if you accept you can flip them and rotate them as well, all possible parabolas can be realigned to have their turning point at the bottom on the origin. But now, to show that they're similar, we have to show we can scale them evenly in every direction and map any parabola onto any other parabola. And here I have put two as different as I really can. I've got y equals ax squared, a nice skinny one up there. And I've got y equals bx squared, a much flatter one there. And surely, to map one of these onto the other one, we're going to have to squash it more in one direction than the other. We're going to have to change the aspect ratio of one of these to get it onto the other one. I mean, look, if I take one point here on the first one, so that is the point y1, x1, that is a completely different point. I mean, look at that rectangle compared to, let's have one out here on the other parabola. That's going to be x2, that's going to be y2. There's no way I can prove there is a common scale that would take that rectangle, that point, and map it onto that point. These parabolas cannot be similar. Sorry that I've misled you. But hey, let's give it a go anyway and see what happens. Right, so we've got the point x1, y1, which is on the parabola y equals ax squared. That's the skinny red one. We're now going to scale both of them by exactly the same factor, k. So x2 is k times x1, y2 is k times y1. It's going the same dilation in every direction. Is x2, y2 on the wildly different parabola y equals bx squared. Let's start by taking our scale factors all the way over here, rearrange them to be x1 equals x2 on k, y1 equals y2 on k. We now know the relationship from the first parabola that y1 equals a times x1 squared. We can substitute those in. Y2 on k equals a times x2 on k all squared. This side can be cleaned up very easily just by squaring everything, so that now equals a on k squared times x2 squared. Oh, we got multiple k's going on. Let's get rid of one of those. So if we multiply both sides by k, we have y2 equals a on just the 1k times x2 squared. I mean, that's nice. That shows us that if we scale it evenly in all directions, our original y equals ax squared parabola does give us another parabola. But is it the same as any other given second y equals bx squared parabola? Hang on. When we started our two wildly different parabolas, I just gave them a and b, and a and b could be any two real numbers. Then down here, what if I now set k, our scale factor, to be a divided by b, which is just another real number? If we scale the first parabola in every direction by a on b, if I put that in there, it equals, well, it cancels out. That would give us b times x2 squared. That means that x2, y2 are on the second y equals bx squared parabola. We can map any parabola onto any other parabola by scaling it evenly in every direction by a scale factor of a on b. All parabolas are similar. There is only one true parabola. No! Gloria in extremis. One.